Hi guys, so in this video, we will be covering on the basic of stress and deformation analysis for machine design. In order to have better understanding of the concept, we are going to revisit some fundamental theory that you have learned during your statics course. I really hope that you still remember the content of that amazing class. Amazing ke? So anyway, we are going to look into the concept of stress, including normal stress, bending stress, shear stress, the stress element, and after that, we'll be looking into the theory of material deformation. Stress is a measure of material's resistance to external load. The material, kalau boleh, dia tak nak berubah bentuk langsung. So, when you apply some load on a material like this, the load that you apply is known as an external load. External because the load are being applied outside of the material. So, outside is external lah. Okay. In response, the material will resist the effect of the external load. And if I can replace the material resistance with an arrow, this is how the material stress would look like. The more area affected by the external load, the higher the stress there is, as there are more area of the material will try to resist the load. Normal stress are the resistance of the material when normal load is being applied to the material. Normal load means the direction of the external load is perpendicular or 90 degree to the surface of the material. Example of a normal load is when the material is in tension or in compression state. Normal stress can be calculated with a very simple relationship of stress using the symbol of sigma equivalent to the force divided with the area. For example, if this square beam is being subjected to a tension load of 500 Newton and it have a cross-section of 20 by 10 millimeter, so the total area of this square beam subjected to the axial load is 20 multiplied with 10 millimeter, and you will get an area equivalent to 200 millimeter squared. Using this information, you can then calculate the tensile stress using the given formula of F divided with A, whereby the force is 500 Newton is already given, divided with the cross-section area of 200 millimeter squared, and you will get a stress value of 2.5 Newton per millimeter squared, or this is also equivalent to 2.5 megapascal. So megapascal is a measure of stress. So you see, senang je kan? Bending stress, on the other hand, is when the material is being subjected to an external force which causes the material to bend. Usually, we will call such external force as bending moment. Okay, we want to differentiate bending force with a normal force. Okay, when it comes to bending, usually the bending mechanics would happen along the flexural center of the material or the beam as shown. Okay, the red line there is called the flexural center. In the bending state, some region of the material over the flexural center would be in compression state, while the opposite region would be in tension state. The location of the flexural center depends on the cross-section of the beam. For circular or square beam, its flexural center is exactly in the middle of the cross-section, while for other non-symmetrical beam, the flexural center may not be exactly in the middle. Bending stress can be calculated with the following equation of moment multiplied by C over I. M is the bending moment, C is the center distance from the flexural center to the outermost layer of the material, and I is the moment of inertia of the cross-section. The moment of inertia again depends on the cross-section of the beam. The formula for different cross-section can be referred back from your statics course. Okay, buka balik buku lama. Shear stress is the tendency to cut an element by exerting a stress on one face and another stress on the parallel face in opposite direction. So if we look into this diagram, the screw and the wood diagram, the pair of the wood is pulling the body of the screw in opposite direction. The pulling effect is the external load subjected to the body of the screw. So if we remove the wood element which caused the external load, then we can see that the direction of the corresponding stress in the material is in the same direction as the material surface. Tak sama macam the normal stress previously. And this situation, my dear friend, is what we call shear stress. And the symbol for shear stress is tau, bentuk macam huruf T tu. The shear stress value can simply be calculated similar with the normal stress calculation, whereby shear stress is equals to the external force divided with the cross-section of the material. In order to analyze a solid element, for example, if you want to analyze some machine component like this, then the computational process in finding the value of stress cannot be performed on the whole object, especially if the object have a very complex features. So you imagine, how do you want to determine the magnitude of stresses at this profile yang banyak lekuk-lekuk ni? Susah kan? So, in order to simplify the calculation process, then the object has to be partitioned into smaller elements of simple shapes, such as the hexahedral element like this, so that calculation can take place. If you are used to designing a 3D model using computer simulation software, then if you want to proceed to structural simulation analysis, you have to partition the solid object into smaller elements called mesh. If I take out one single mesh element from the solid model, then it may look something like this. Each surface of the element will have its own magnitude of stresses. The stress may be in normal stress, it can be either in tension or compression, and it can also be the shear stress. So you imagine, compared to the full body geometry, the calculation of stress would be much more easier if the element is like a simple hexahedral shape like this. Remember the exercise that I gave you last time on material selection? If I may recap, you need to select a material for a gear housing which can sustain a stress of 100 megapascal. So that 100 megapascal is the external stress subjected to the gear housing. So, of course, when you want to select a suitable material, the yield stress of that material should be higher than the stress caused by the external load, meaning the material can sustain the external load without reaching its deformation point. If you look into the given element, the yield stress of aluminium is 1 to 5 megapascal and the yield stress of steel is 2 to 8 megapascal. Both have higher yield stress than 100 megapascal. So theoretically, you can select both material. But realistically, material with higher yield stress may be more expensive. So kalau tengok dekat steel, the yield stress of steel is 2 to 8 megapascal, almost twice than the amount of 100 megapascal limit that we need. From the perspective of design engineering, if you select steel as the material, you may over-design the machine element as you can actually select material with lower yield point instead. And still, it won't deform. So ideally, in this case, selecting aluminium would be the best choice. If you are confused with the concept of material selection, then feel free to drop your comments here. Okay, as an exercise for the attendance of this particular lecture series, determine the type of stress exists in between the pin and the blade joint. Okay, that is all for now. So in the next video, we will be looking into the concept of combined stress and Mohr circle. Okay, so stay tuned.